Should we welcome people?
Welcome people back. I think so. I think it's been a while. And I think this episode deserves a little bit of like setting the stage of what we're doing today. One, because it's been a really long time. But two, the reason this should have been released a while ago, but we lost some of the audio. So we are re-recording an episode. I think it's important because we're probably going to reference the first one, like, say something like, when we recorded it the first time, you said this or something like that. So that's the context for it.
Right. Yeah. And future episodes will say, if we didn't re-record this, we'd be talking about, that time we did Bell's theorem, and
exactly
you wouldn't know what we were talking about. So
yeah, we had to get this one re-recorded before we could release the next one. So yeah, so this episode, what I'd like to talk about today is Bell's theorem. And I did listen back to my side of the recording that was able to be listened to. We didn't have yours, but it was interesting to listen back because I started it by saying, I've studied this like 6 times in my life, Bell's theorem. And every time I study it and try and figure it out, I'm like, yep, nailed it, got it. And then I completely forget it like the next day. And I felt pretty prepared in our last recording, and like I understood it really well. But then I went back because I'm like, we're going to re-record Bell's theorem. I should like refresh my notes. I'm like, I don't remember at all what the point of Bell's theorem is again, like after even preparing it. So I don't know. There's something like oil and water with my brain and Bell's theorem that like the point of it just doesn't stick. And I'm going to say it again. I think I got it this time, but ask me tomorrow and it might just be gone. So yeah, I don't know how you feel about Bell's theorem.
I tried to remember exactly, like this time looking at it, when I went back to like look at notes and stuff, I thought, okay, I kind of remember some of it from last time. And I knew the things to Google and like refresh my memory. Whereas like the last time I was kind of just limited to only Bell's theorem and then had to work my way from there. So like it didn't fully stick with me either. I think it's because it's kind of a weird concept that like gets viewed from a lot of different angles,
right?
And talked about in different ways. And so like you could read one topic that's talking about it from one point of view, and then you read someone else and they kind of tackle it from a different point of view. So trying to make a coherent picture, I think, is a little difficult with Bell's theorem.
And I'm going to say I hope to do that today, but who knows how well it's going to come across. But I think I've distilled it even better from the last time we recorded. I think I have a better understanding of the main point of it, and I can separate the ideas that get conflated around Bell's theorem and make it, I think, a little more concrete in the historical context of where it comes from. So that's what I hope to do today. Last time we did get wrapped up in the weeds of like spin operators and like projections with like up and downs and left and rights, and it got pretty difficult to listen to. So I'm going to try and make a conscious effort to avoid that unless you take us there, and I'll like try and keep us on track and remember where we're headed. But I don't want to get into the math too much, and the math I don't think is super interesting. I think the philosophical implications are pretty much the meat of Bell's theorem.
Yeah, I kind of, I read, actually I just read Bell's paper.
Mm-hmm.
And like reading that was not very interesting or very enlightening or anything like that.
Yeah, I agree. I mean, it is, but I think it takes a filter to like get through what he's actually saying.
Yeah. I had to like reference other sources to then like, because his paper is like, here's a bunch of math,
mm-hmm.
and like to derive the implications from it. Like I don't have that quantum like confidence
right.
to just like, I get it.
He's making really, 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 really subtle arguments in math, and it's not that the math is hard, but you're just constantly asking like, why did you have to go this route to make that such small point? Like that's where I always get tripped up in the derivations and like leading to the inequalities. It's like there's such subtle arguments that just it makes it really difficult to follow and like wrap your head around not only the math but just like the philosophical implications of the math.
what I ended up doing was there was a paper by what's his name? David Mermin Mermin. That was fairly decent on the topic.
Right.
It kind of like gave me bouncing between that and Bell's paper, and then just reading like the Wikipedia pages. I was kind of able to piece things together.
Right.
In a pretty decent amount. I mean, just to kind of tease what you guys are going to listen to, we've been talking about what we're going to talk about for a while, but just, some teasers is like some people have, I think it was I don't think it was Berkeley or Lawrence, but it's been quoted Bell's paper as like the greatest scientific like finding of the 20th century. It has a lot of pretty cool implications for such a small, like the actual paper is 1, 2, 3, 4, 5 pages plus references. Like,
right.
It's a pretty short paper. So but it has like a lot of deep meaning to it.
Exactly. Yeah. And the not the best textbook on it, but a textbook that I can read and follow decently, Griffith's Quantum. It talks about Bell's theorem, I think, in the appendix, because it's kind of like an add-on to the book, not required for the rest of the book to understand it. And I think it's a half a page. Maybe it's 2 pages at the most in that textbook. And that's like the proof of Bell's inequality. So it's not that hard, but again, it's just these subtle little arguments. And people have since distilled it quite a bit into like the essence of what he was actually getting at. And so I think we benefit from that in that there's been a filter of time to help us kind of clarify what's going on there. And the original paper, like you said, it's 5 pages, but it's got a lot of math. And if I remember correctly, the math isn't even like the quantum part of it isn't difficult. The math is pretty straightforward in the quantum part. But then when he gets into we'll talk about hidden variables, when he goes through that math, I think it's pretty rough. Like it's hard to follow what he's talking about.
Yeah. Well, he's very much just like, here's an equation, here's an equation, here's an equation. Let's mash these equations together without a whole lot of like physics in it. Right. He doesn't say like, okay, here's what the meaning of or interpretation of this question, because he's not writing for someone like me who's reading it. He's writing to other, doctors of physics. I'm
glad you brought up David Mermin, because I think he plays a big role in my understanding, in that I've read some of his papers, and a lot of the YouTube videos and the pop science interpretations or explanations of Bell's theorem goes along with Mermin's explanation of it. And he really distilled it in a really simple way. And I think he completely deviates from what Bell actually did in Mermin's thought experiment. It's a totally different setup, and it's a lot more straightforward and easy, and kind of just like counting, as opposed to Bell's, which is integrals over density functions of hidden variables. I don't know. It's a lot simpler when you're just counting possibilities.
Right.
And so that's Mermin's take on it. And that was one part of the confusion. And I said it in the last recording, and I want to say it here again in particular. A big part of my confusion early on, or like going through, I don't know, undergrad and grad school and stuff, and learning this and trying to watch other YouTube videos and pop science articles about it, they don't say that they're doing the Mermin version of the experiment, because I would try and derive the Bell's theorem from Bell's version, and then watching pop science YouTube videos, they all do the Mermin one, which is simpler, a lot simpler. And like I said, it's just straight counting. Sometimes people do the like Malus law of like a particle going through a polarizer, something like that, and that's where they derive the angles. And that's what Bell did. But then the Mermin one is just, here are 3 possibilities, and they're all equally spaced around a unit circle, and you just count what's up and what's down, and there's only so many possibilities. If there are hidden variables, you get one answer. If there aren't, you get a different answer.
Great.
And that's
going to be interesting to talk about, because I kind of have a vague understanding of both Bell and Merman, but I don't feel like I have a solid of either. So I'm going to learn something.
Cool. So let's get into the history of where this comes from.
Yeah, I was going to say, should we start with like EPR or
exactly
Heisenberg's uncertainty principle?
Well, yeah, we can go back to Heisenberg. Let's start with EPR and explain why EPR came about. So EPR stands for Einstein, Podolsky, and Rosen, who wrote a paper in 1935. And it's the Einstein and then two other physicists, Podolsky and Rosen. But they were trying to highlight an issue with quantum mechanics, which was, in its, I don't know, not teenage years, but, if you say quantum started in 1905 and then they're now in 1935, it's 30 years old. And it's pretty well established. And the 20s really helped solidify the math behind it, the foundations of quantum mechanics. And so they've had about 10 years of solid math backing up quantum mechanics, and people were on board. Einstein, Podolsky, and Rosen had conversations about problems with it, namely the Heisenberg uncertainty principle, which has, in one version, you can talk about position and momentum not able to be measured to infinite precision in an experiment. So there's always going to be some uncertainty when trying to simultaneously measure position of something and the momentum of something. Not super important, the details of that, but that's the foundational issue that they're trying to wrap their heads around.
Yeah, maybe I just want to add that, if there's the technical term is two commuting operators, but that aside, right. There's particular things that you can measure that you can actually know both at the same time. And there's other things that you can't. And position and momentum are two of the things that you can't know both exactly at the same time. And there's other options out there too, as we'll get to.
Right. And so what EPR did in their paper, and I just want to put this side note in, I read something that, so Einstein didn't technically write anything in that paper. It was mostly Podolsky, I believe, the P part of EPR. And there's an English typo in the title, and they say it's Podolsky being Russian. He didn't speak fluent English, or his English wasn't perfect, and so he had a little hiccup in the title. Anyway, Einstein has said that his views weren't actually captured perfectly in that paper. There were still issues with the philosophy of the paper that he wished he could iron out, but it was published with his name on it. It captured well enough for him to be okay with it to be published, but I think that adds to the confusion in that we don't even get what Einstein was really frustrated with in quantum mechanics in the paper that everyone's talking about.
Apparently, there's a lot of back and forth between him and Born, Einstein and Born, that you can read, that he tries to kind of explain his problems further. And right. From kind of what I've read, I haven't read their actual letters back and forth, but just kind of about their letters back and forth, Born got kind of annoyed with Einstein, just he couldn't explain it well enough.
Einstein couldn't explain it well enough to Born.
No. Yeah, Born couldn't explain it well enough to Einstein to get him to understand why Einstein shouldn't have problems.
Right. So let's get the historical context. A lot of people say the issue that Einstein had with quantum mechanics was that the God doesn't play dice, right? That's kind of a pull quote that people often use. I think historians, scientific historians and people who look into this, agree that Einstein was fine with that. He didn't really care that there was a probabilistic nature to quantum mechanics. That's fine. What he really didn't like was what the other quote that comes from this whole discussion, which I think was in a letter to Born, where he wrote he didn't like the spooky actions at a distance. That's what he didn't like. And it wasn't that he was nervous that special relativity was at risk of going down the tube because all of a sudden something can travel faster than light. He understood this wasn't actually information being sent across huge distances, which we'll talk about what I'm talking about in a second. But that quote, the spooky actions at a distance, that was the fundamental issue he had with what quantum mechanics was saying. It's there's some influence that's happening over huge distances. You can't send a signal with it, so it doesn't break special relativity, but that's what his big problem was. So the EPR, I don't even want to say the word paradox because I don't know that it is a paradox, but what they try to outline in the paper was an experimental setup, and it's extremely elaborate and complicated, but essentially they have two systems that start far apart from each other, come together, interact, like collide or something, and then separate again. So, I mean, in the simplest terms, two baseballs far apart, colliding, and then separating in space, something like that. Something straightforward. And then what they said was measure the position and the momentum of one of the systems. And because somehow you knew the initial conditions, you know that momentum has to be conserved, you can deduce what the position and momentum of the other system is without ever measuring it, right? That's pretty straightforward. Like with baseballs, you could do that, and it's not hard. And we do actually do that in like basic physics classes. You have little air tracks and the carts collide, and you use conservation of momentum and energy to figure out speeds of the other carts, stuff like that, right?
Yeah.
All well and good in classical mechanics. What the issue they had was in quantum mechanics, the position and momentum aren't well defined. But by measuring one system, you can get a well-defined position and momentum of the other system simultaneously. And so they said there's some conflict. And that was at odds with the uncertainty principle. And so they said, quantum mechanics says there has to be an uncertainty, but and this is a little bit of a misrepresentation and simplification of what they thought, but EPR was saying the position and momentum of a system has to be measurable, but also independent of the measurement, meaning it has to exist before the measurement happens. Like they kind of were just like, it's just logical. Like that's the case, right?
Yeah. So let me see if I can like say this in a different way slightly. Is that like,
sure.
Okay. So if you have these two things interact and then they separate, and you can measure the, momentum of, let's say you have system 1 and system 2. You can measure the momentum of system 2 and then therefore deduce the momentum of system 1.
Mm-hmm.
But then it's like you know both of those things instantaneously and then additionally, like you can also like, okay, so one of the maybe I'm mixing things up here, because you can measure the momentum of system 2 and know what system 1 was, and you can also measure the position of system 1 and know the position of system 2, and therefore
right.
You know everything about the system exactly.
Right.
Okay. Well. Okay. Yeah. I'll let you take it.
So there's a physicist named Tim Modelin. Have you heard of him?
No.
Have you heard his name?
No.
I recognized his name. I don't know where I know it from, but I watched a YouTube video of his. It's a talk that he gave somewhere. And he kind of explained it that you don't even need to go into the uncertainty principle. Like quantum mechanics, you can talk about positions. And like if you measure the position of system 1, you immediately know the position of system 2, even though quantum mechanics might have a wave function of a distribution of positions for system 2, right?
Yeah.
So right there, you don't even need to go into momentum is his point. Like they could have just stuck with position, but maybe the argument wouldn't have been as elegant. I don't know. So
is the problem here that if you measure system 1's position, mm-hmm. and then you instantaneously know position or system 2's position, and that's the spooky action?
Exactly. Like the system 2 had its own wave function that had a distribution of positions where it could have been. But by measuring system 1, you immediately collapse the wave function of system 2. Done. You don't even need to go into momentum or uncertainty principle. That's one way to think of it. And that's not what EPR said. They did go into the uncertainty principle, like you were saying, like cross-measuring position of 1, momentum of 2, the opposites.
Right.
And so you can break the uncertainty principle that way. But you don't have to go that complicated.
Yes. And so the thing Einstein didn't like is just that there's okay, so if you measure system 1's position, then you instantly know position 2. So either that wave function collapsed at this exact same moment, or it already had a definite position.
Right. Like it was pre-programmed, like some DNA inscribed in a particle or a system, doesn't matter what it is, that the second the particle came into existence, when you make the measurement of where is system 2, it's already known by the particle, by the system, the answer to that measurement. It's prescribed. And we just don't know it. And quantum mechanics can't know it. Quantum mechanics says it's unknowable. Einstein was saying it must be just a hidden thing that our technology can't probe yet. And we don't have an explanation for it. But he's like, just call it a hidden variable. I don't even know if he used the word hidden variable. That might be another distillation through time. But, there is something we don't know, we can't know, but there's something there.
Right.
There must be. Right. Because there has to be, and this is what gets at the heart of the philosophy of it, there has to be an element of reality to the position of an object at a given time. Because he was saying everything must have an answer to these questions ready to go whenever you ask them.
Right. Yeah, I think
that's the crux.
I think maybe to make this a little more concrete, that we let's move forward in time to like the Bohm or Bell version of this, if you're ready.
Let's highlight the three kind of assumptions that EPR made, and then we'll see how Bell knocked them down. There's lots of different ways to look at this, and then we'll get into what you're saying exactly of how we move past the systems of colliding and position momentum and stuff, and get into what most people think of as the EPR paradox and Bell's theorem regarding that.
Yeah, I guess the thing I wanted to like make a little more concrete is it seems weird to like, if you don't have any experience with quantum mechanics, it seems intuitive to say that you're going to know what the position is at a different, based on the interaction of the two, just because like you said, like with baseballs, we know that works. Mm-hmm. So, right. In order to like maybe make it a little more mystical until we talk about it, is that there's some property of these particles that we can't know both of at the same time. It doesn't have to be position or momentum. It could be something else. Right. And it's, quantum mechanics says we can't know both of those things. And Einstein's proposing, well, if we measure one, then we automatically know the other. And either it was already going to be that way ahead of time, or there's a spooky action at a distance, and he didn't like that.
Right. So let me read the definition that they put in the paper, in the EPR paper, of reality. And this is what the crux of the whole thing is. And this is why it touches philosophy, because they get at the heart of what is real. And that's it's deeper than physics, I think, right? It's just like, what does reality mean? And whenever anyone talks about, stupid stoner questions in physics, they're always like, well, what is real? They get to that point. But this is what they were doing. Right. So they tried. So what they did in the paper was try to define reality, and then they showed how quantum mechanics doesn't fit that definition. And so there must be something else to give systems real properties. So their definition: if a property can be predicted 100% without disturbing it, then it is real. And that's a paraphrase. They used more words than that, but that captured most of what was said. And people argue about the choice of the language, the word disturbing. What does that mean? But if a property can be predicted 100% without disturbing, then it is real. So a property that can be known without making a measurement. So I think of this as the freshman physics momentum collision carts experiment. You can predict with 100% certainty, following classical mechanics, what the position of cart 2 is after it collides with cart 1. Something like that, right?
Right.
The problem is, in quantum mechanics, there is no 100% certainty. You're always left with the probability distribution. You're always stuck with some uncertainty. That's what quantum mechanics says. So that's the crux of the issue. Quantum mechanics isn't enough to give us a physical reality based on their definition of reality. Does that make sense?
Yeah.
Like, that's a straight quote from their paper. I mean, that's not exactly word for word quote, but property can be predicted 100%. It's real. So in kind of distilling EPR, Bell got to the point, and I'm jumping ahead, but I just want to get to the assumptions I think that Bell was trying to take down. He said that a theory that explains, what EPR was proposing, it should agree with experimental predictions. It should agree with special relativity. And there should be simultaneous elements of reality. And I think he's just kind of capturing what EPR had issues with. That the special relativity part, I kind of added that, but that's essentially what most people call locality. Like you can't affect something at far distances instantaneously. Agreeing with special relativity means you need a time to propagate information to cause some sort of disturbance, some effect to lead to the results of a measurement based on another happening somewhere else.
Yes.
Right.
So some form of energy can't travel faster than the speed of light.
Right.
So, therefore, if, essentially if you and I are 1 light minute away, that's the distance light travels in a minute, then I can't know what you were doing until a light minute has passed or a minute has passed.
Right.
It takes time for something to travel to me.
Mm-hmm. So yeah, that's what most people talk about as the locality crux of the EPR, where they want to hold on, they want to preserve that concept of locality, which is essentially being in line with special relativity. The other one, though, is the realism part, and that's kind of their definition of reality coming into play, where the position and momentum of an object should be known. Like there are positions and momenta of systems at the same time. Like, right? Like a system, just intuitively, it should have a position and a momentum at the same time. Quantum mechanics is the problem. It's not that the system doesn't actually have that uncertainty. It's that if we just don't know it. And that's, I think, really what Bell was tackling, was that realism argument, that the states have, that the answers to certain questions are already determined and are able to be determined with 100% precision before a measurement even comes in play and disturbs it. The locality thing is what a lot of people focus on, but I think the realism one was the real Bell, what he was taking down with EPR. Okay, so that was EPR. Two systems colliding, position, momentum, uncertainty principle, 1935. Nothing really happened. I shouldn't say nothing really happened. There was a huge debate about this, and Bohr chimed in with a paper, and he titled it the exact same, and he even used the same improper English in his title. Yeah, it's not a spelling error. It's like the grammar was weird.
Okay.
I don't know. Yeah, I should look up what the paper is. But anyway, he used the exact same title, and he published a paper. And if you don't even read Bohr, but you read people talking about Bohr, Bohr was notorious for just completely being unclear in his wording. And like, if you read it, you're like, everything's there, but man, does that not crystallize into like a coherent thought for me? Like, he's very wordy and just, spirals and spirals of huge sentences that like eventually land on a point, but he was just tough to understand. But him and Einstein were the kind of two top guys that would go back and forth against each other in like a respectful, professional way. Like, they didn't hate each other. They would just, would have philosophical differences, namely the EPR paradox, or I keep calling it the paradox, the EPR argument. And then Bohr was saying, no, it's just what quantum mechanics is. Merman has a talk on YouTube that's fantastic. I highly recommend people watch it. I think it's given at Berkeley. And he's so good at clarifying everything, and he just puts in the simplest words. Like Feynman was always good at this too, like just using really plain English to just say something extremely complicated.
Yeah.
He has quotes from Bohr, and he just puts his own words in brackets to make it really clear. And he calls, instead of saying system 1, system 2, blah, 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 he says there's a thing, and then there's the stuff that's left behind. And that's like supposed to be system 1, system 2. And so he takes Bohr's complicated sentence, and he just replaces everything like systems and measurements and, technical terms, and just drops in the thing and
right.
The stuff left behind and the testing. And like, he just like throws in really basic words that totally captures the main point of what Bohr was saying. So I highly recommend watching Merman's talk.
And if you want to know, the title of the paper is "Can Quantum Mechanical Description of Physical Reality Be Considered Complete?"
Yeah. So, you could put the word in there.
Yeah.
Quantum mechanical, but he didn't have that. And then Bohr wrote the paper with a counter paper with the exact same title, which is really funny.
Which would make sense for a Russian, but not for Bohr. Was what, German, I think?
I think Bohr was
Dutch.
Danish.
Yeah, Danish. That's it.
Yeah. And Bohr's writing is very good. Like, he's very well written, and like his English is good. But anyway, it's just very long. He needs an editor, I think. But anyway, who am I to judge? I'm definitely in no position to. But I also think Bohr answering it adds to the confusion because of his long-winded reply. And, you know, people interpret what he says in kind of like a Rorschach test, like you see what you want. That's definitely an extreme position, but he was nebulous enough that people could interpret what they wanted from his reply. And I think Bell, in the Merman talk, he has a quote from Bell saying Einstein was so far ahead of Bohr in his understanding of the problem, and Bohr just didn't really address the actual crux of the problem. Bell really thought Einstein had an amazing point. And people look back and say, like, oh, Bell proved Einstein wrong. And that wasn't what Bell thought he was doing. He just thought Einstein was bringing up a point that was important for people to consider, and no one really took him seriously. Bohr just said, no, physics is right, quantum mechanics is right, because I said so, essentially, you know, because the math works, right. because we're okay with this. And then Einstein was like, I'm not okay with this.
Yeah, I mean, it was essentially theory agrees with experiment.
Right.
We're fine, you know, and Einstein wanted to say, well, I think there's something deeper than that.
Right. Have we thought about what this really means?
Yeah.
That's basically what Einstein was saying. And Bell took him seriously and like went through a rigorous proof to show that it's not that Einstein was wrong, but that quantum mechanics can exist without the EPR definition of reality. So the like, what is reality is unanswered still, you know. That's basically what Bell showed. And Einstein was saying, hey, we got a problem with reality. And so Bell was kind of agreeing with him, but showing that like quantum mechanics can definitively say that there's a problem with reality, at least that definition of it. So, again, the Bohr wording has led to a lot of confusion, I think, with what the argument was. And it kind of sat there from 1935 until about 1951. Bohm, B-O-H-M, was another physicist. I think he was American. I could be wrong on that. I'm pretty sure.
I think so.
He definitely was in the U.S. and the professor in the U.S. And we have an episode coming out about his theory of quantum mechanics, or his interpretation of it soon. But he took the position, momentum, systems colliding arguments from EPR. And he's like, you know what? We can do this more simply if we consider a system that doesn't come in from distances away and then collide, interact, and then separate again. Like the EPR was a scattering argument, which is pretty complicated. Bohm said, let's just consider something that starts at rest in some frame of reference, a system, and then it explodes, essentially, and we have two fragments going off in opposite directions. And he used a hydrogen molecule and the H2 molecule separating somehow, and we have two hydrogen atoms now flying off in opposite directions. They started from rest.
He used a what molecule was the first one?
A hydrogen molecule, H2.
Wait. Okay. All right. There we go. Molecule was the word I was missing.
Yeah.
Atom.
No, and so he what he originally used, I thought it was an atom or a nucleus or you know, something, which is what most people talk about, but that's again a distillation from time. But the original argument that Bohm used in his, I think it was a textbook actually, was a hydrogen molecule. Gotcha. So two hydrogen atoms in a molecule, somehow disassociating. Who knows how? They just spontaneously decide to separate. The molecule started with zero angular momentum and zero momentum. Pick a frame and then just say it's in the singlet state. So the spins of the hydrogen, we got it in a spin. I said spin for the first time. Angular momentum is conserved from this separation. If there was zero initial angular momentum, that means that the one that went to the left and the other hydrogen atom that went to the right have to have opposite angular momentums. We can talk about what it is, but it doesn't matter. Let's say the one that went to the left had an angular momentum of 5. That means the angular momentum of the one to the right had to have a value of -5 to add up back to 0.
Yeah,
exactly. The key is that they're opposites. So that's kind of the way we think about the EPR paradox these days. But again, it wasn't what EPR actually did. So I'm going to talk about spin, and we're going to get into the Merman version of this and the way most people talk about it also. But we should just define spin real quick in a simple way, and just think about like the spinning basketball or spinning top. So if you think of particles spinning and a direction that their spin might point and a value it might have, the faster it spins, the bigger the angular momentum, the bigger the spin. And if it's rotating, say, clockwise, it would have a positive value. And if it's rotating counterclockwise, it would have a negative value. So the faster it spins, the bigger the number, but then the clockwise, counterclockwise tells you which way it points. Does that make sense? It's the real quick and dirty way to explain spin.
Yep. Yeah. And it's just it's a property of particles that they have spin.
Right. Yeah. And I mean, in Bohm's version with the actual hydrogen atom, it's a little more complicated because it's a composite system already with particles. Like there's a proton and an electron in the hydrogen. Whatever. It doesn't really matter that much.
And it gets reduced even further in history to just being a positron and an electron pair.
There you go. Exactly. So those are individual particles, and you don't need the complications of a hydrogen atom. It's just a single particle going one way and a single particle going the other. And really, all you have to worry about is if one is what we call spin up, the other one has to be spin down because it has to add up to 0. That's how we talk about it these days. So again, that was Bohm in 1951. And so it's about every 15 years. 1935 EPR, 1951-ish, 51 is Bohm. 15 years later, 1964, I know that's not exactly 15, but we get Bell, his paper, publishing the mathematical proof, you could say, that quantum mechanics is, or basically he came up with a way to demonstrate experimentally and settle the EPR question. Is quantum mechanics the correct way to do this? Or is there a hidden variable that's existing along with these particles? Is there some sort of DNA inscribing the particles that we just don't know anything about? And that's really, he just starts from that assumption. Let's assume there is a hidden variable. Let's go through all the math to show what that would mean for our experiments. And then he ends up with an inequality. He says, if there are hidden variables, this inequality should hold. Measurements on this system or in this particular way should be greater than or equal to measurements in this particular way. Right?
Yeah, it's pretty interesting that what he came up with was a way to differentiate whether the quantum mechanics was right or classical, if you want to call it that, the hidden variables idea, but like kind of in a way that just didn't seem like I feel like his argument isn't particularly it's not a crazy thing to have thought of, I feel like.
Mm-hmm. Right.
But he just did it. So I feel like it wasn't crazy to think of, but the outcome was unexpected.
Right.
And it's kind of interesting in that regards that, hey, okay, we can tell the difference between quantum mechanics and this hidden variable thing by this inequality.
Mm-hmm. And namely, he gave a prescription for experiments to be run to actually test it. And that's, I think, the big benefit. People always look for the ways to test theories experimentally. His paper was an outline of an experiment to run. So we can go into the details slightly. I don't want to get too bogged down with it because, again, it's the result is really the main important part. But it comes back to those spins we were talking about and one having to be up and the other having to be down. It gets a little weirder instead of just up and down, but you try and measure it at like a little bit of an angle. So there are ways to measure spin with magnets, or some people talk about photons with polarizers. It doesn't really matter. There are ways to measure spin. But the key thing is with the spin of an electron or positron, it can only be plus, meaning up, or negative, which is down, in whatever direction you want to measure it. So if you set up a spin measuring device to measure something vertical, the spin vertical, which is the way most people talk about it, you'll get up or down. But you can rotate it to measure the spin in a horizontal direction, which, what would that look like? It's kind of like if you spun a basketball with your fingertip pointing towards the wall instead of the ceiling. And however, a basketball could spin that way, but that's what that would mean, measuring the spin in a horizontal direction. Is it spinning clockwise or counterclockwise with your finger pointing towards the wall, parallel to the ground? Does that make sense? I know it doesn't make sense for basketball, but for particles,
like if you're in space, just picture it in space.
Exactly. So you can set up a detector to measure, is the spin up in this horizontal direction, which doesn't make sense in English, but that's how physicists talk about it. Or is it spin down in the horizontal direction? And the key thing is, again, we're all assuming conservation of angular momentum. You know, that's something no one talks about. What if conservation of angular momentum is wrong? And we just throw out the whole problem. And we solved it. Just kidding. No one thinks that. That's absolutely not up for debate. But the thing is, if you measure a horizontal direction and you get spin up for one of the particles, you're going to always get spin down for the other one because of conservation of angular momentum.
Yeah, but I think a really maybe crucial part to say too is that just like position momentum, how we talked about earlier, you can't know either one exactly. Mm-hmm. You can't know both of these spin ups. You can't know the spin horizontally and the spin vertically exactly at the same time.
That's right. That is a key part. That the quantum mechanics says there is an inherent unknowability. If the particle to the left you measured in the vertical direction, and you got up, but you set your detector in the particle going to the right, so you set that detector to measure the horizontal spin, you have no idea what the answer is going to be. It's unknowable, it's unknown, it's 50-50 shot up or down. It has no correlation to the vertical direction, which goes back to the EPR talking about position and momentum. There are fundamentally conflicting knowabilities, and the spin's just easier because it's a basically yes/no question. But and that's why that's the one most people talk about, because it is such a conceptually simple setup compared to EPR.
Yeah, and one like interesting property about this, at least I think, is that like if you separate these two particles, right, and we said, okay, if I measure the spin vertically up, then we know that the spin is vertically down for you. Mm-hmm. But if I measure the spin horizontally up, there is no way to know what your spin vertically up or down is.
Right.
It's when you just can't. It's 50-50.
It's a 50-50 shot. Right. Exactly. Let's touch upon one thing, and then we'll get to the Bell experiment and how this comes about. But the one thing I want to touch upon is the spooky actions at a distance, which talking about a particle going to the left and say you're going to measure it in the vertical direction. Which way does it spin point, up or down? You don't know. But let's set the detector on the moon for the particle going to the left. Then you set the detector for the particle going to the right, somewhere in outer space, could be in the Andromeda galaxy, doesn't matter. I'm just trying to make big distances. It doesn't matter how far they are. If you measure the one that went to the left spin up on the moon, and then you didn't even ask, but you just waited for the person on the Andromeda galaxy to measure it and come back, you know for certain that they measured it spin down if they measured in the vertical direction also. But quantum mechanics, the problem is quantum mechanics says the second that particle's on its path to that detector, it's a 50-50 shot. There's no way to know if it's going to be up or down. Doesn't matter. The left particle doesn't come into play yet. It's just if you only focus on the particle that went to the right, quantum mechanics says 50-50 shot up or down. But the second you run the experiment for the particle on the moon, the one that went to the left, and you measure up, the one on the right is always going to be down on the way to the Andromeda galaxy.
Yeah. So I feel like this is a easier way to kind of think about it. And I think that's why most people don't necessarily look at EPR the way EPR is discussed. Mm-hmm. But, like if you think about what you just said, a simple conclusion is to say, oh, well, the one that you were measuring on the moon was up ahead of time, and the one going to Andromeda was down ahead of time.
Right.
Like that seems like an obvious statement to make, is
right.
that, we didn't know what it was, but like the universe knew, or the particle had it, instilled in it, it was always going to be up. It had the property of upness, spin upness to it.
Right. Yeah. And that's, people just assume, like, let's not use particles and weird stuff, but let's take, I think people talk about like gloves, like a left and right-handed glove. You have a pair of gloves, send one to the moon, send one to Andromeda Galaxy, but they're sealed in boxes. You don't know which one's which. If you open the box on the moon and it's the left-handed glove, what's the one in Andromeda?
It's the right.
It's the right-handed glove, right? Like no, like complicated quantum mechanics. The problem is we know for a fact that the glove was left-handed on the way to the moon the entire time. Like that's just a property of gloves. Like we have the physics of gloves, and it's not like the glove is in some superposition. It's a classical object. The problem is when we get into particles, quantum mechanics describes the rules of their movement, and it's fundamentally unknown if it's an up or down particle until you measure it.
Right. Well, in fact, we say it's not in an up or a down. It's in a superposition of those two.
Yep.
It's both at the same time.
Right. Let's ring the superposition bell. It's the first time it's been said, but that is the crux of all of this. Quantum mechanics says these particles are in superposition states. It's a combination of both up and down. And this now gets at the Schrodinger's cat problem, which was a reply to the EPR and the Bohm papers saying, you guys are right, something is really wrong with reality. Schrodinger saw it, and that's what the Schrodinger's cat is all about, is saying, look, what is the difference between a glove and a particle? What is the difference between a nucleus decaying and a cat in a box? Like, where do we draw the line? And this also gets into the word that I don't really want to use, which is consciousness. Which does the cat have consciousness? Does it know it's dead or alive? But anyway, that's where this leads to, is those kinds of questions. But the spooky actions at a distance are measure up on the moon. Immediately, the one in Andromeda is going to be down. That's just from conservation of angular momentum and from collapsing of the wave function in quantum mechanics. And that does the measurement on the moon affect the measurement in Andromeda? You could say that, but there's no way to really know. I mean, there's no test except when Bell starts doing his little experiment, which is different than what I'm describing.
Yeah. So this is like, maybe now's a better way to phrase what I was saying earlier. This is the kind of, I think the cool thing that Bell did is he said, I have a way to test whether it was superposition or whether it was that way ahead of time.
Right. So the Bell test is what we've been talking about is measure up on the moon, measure vertical spin on the moon, measure vertical spin in Andromeda. If one's up, the other one's down. Zach, you brought up the measure up in the left particle, measure vertical in the left particle, measure horizontal on the right particle. It's a 50-50 shot. There's no correlation. Bell's genius, I don't know. It's such a simple thing, but he went to the logical extreme of what it means to do this. Measure vertical in the left particle, and then measure a slightly different angle, but not horizontal, on the right particle. So set up the detector
in between.
Yeah, at an arbitrary angle, somewhere between vertical and horizontal. Doesn't really matter where. If you do the experiment at particular angles and measure the results at different angles, you will get different answers if quantum mechanics is the true, quote unquote, description of the world, or if EPR's reality, in that there was a hidden variable prescribed to those particles on the way to the detector, and then the detector just made the measurement based on what those hidden variables are. That's it. That's literally the change that Bell made, and then worked out all the math to show that quantum mechanics says one thing, hidden variable says a different thing.
Yeah. So like if Bell said, if you do this experiment a bunch of times, then statistically quantum mechanics will produce this, curve essentially.
Mm-hmm.
And if you do it a bunch of times and it's that way ahead of time, the hidden variables one, you'll produce this curve.
Right.
And so then you can just test that. You can do it.
Do those experiments. Set your detectors at different angles and just measure the correlation between the one that went to the left and the one that went to the right, measuring the one at the right at different angles. And you're going to get results, and you're going to say, did this inequality that Bell proves through the hidden variable assumption, is it held up? And you'll in millions of runs and statistics collected over lots and lots of trials, you'll always come out with the understanding that hidden variables defeat the inequality. Like if hidden variable says answer is greater than or equal to 5, you'll do a whole bunch of experiments and get 4 and 3. You'll always get less than what it says, right? If the inequality says it has to be bigger than 5 to be true, you'll see 4s and 3s all the time. That's the shortest way to say what the inequality is. And when you violate the inequality, then you say it can't be hidden variables. And then when you do the quantum mechanics, you'll always get 4 and 3 right on the nose in theory. And then you do the experiment, same thing. It completely matches what the experiments show.
Yeah. So that means that there's no hidden variables, local hidden variables, and that was spooky. There's spooky action at a distance.
Yep. So the conclusion that Bell came to in this sentence, he said, no physical theory of local hidden variables can ever reproduce the prediction of quantum mechanics. That's it. I mean, just done. Mic drop. It's done. Whew. That's Bell's theorem.
Yeah. And so, but
what does it mean? That's the big, I mean, it's easy to say it's, 20 words before a period and then it's done. But what does it actually mean?
Yeah. I mean, he's essentially, saying that you can, there's different ways to think about this. Merman has a pretty good paper that kind of talks about, but there's no way you can inscribe a set of DNA to the particles ahead of time. No matter how complicated you want to make that process, there's nothing you can do that'll then tell the detector what to measure later, essentially what it's going to measure later. You just can't do that.
Right.
Like the two are incompatible.
Yeah. Yeah. I mean, yeah, so that's Bell's theorem. It's the inequality, but more importantly, it's the violation of the inequality. And then his conclusion is that quantum mechanics and local hidden variables are oil and water. They can't talk to each other. They can't produce the same results, same predictions. So is quantum mechanics correct, or are local hidden variables correct? That's when you go to the experiments, and then everything sides with quantum mechanics. Every experiment, I've seen some papers that are like, we show that quantum mechanics wins, quote unquote, to 400 standard deviations or something ridiculous. Like, there's no chance that hidden variables are at play here.
Yeah, and these. Like every time I think like pretty much after Bell proposed this, people started testing it pretty quickly. Right. Because it's actually not terribly hard to test this. Usually it's done with polarization and not spin, but but someone would test it, and then there would be a response to the paper that said, okay, quantum mechanics is right. There'd be a response that said, oh no, you forgot about this. Like you didn't think about this part. Right. And then they would adjust the experiment and say, oh no, quantum mechanics is still right. And then someone else would say, no, but you forgot about this part. Right. And they would adjust the experiment. And I mean, this was still going on in like 2015.
Well, even more recently than that. I mean, I think they literally last year did a big scientific test of it again, using like the stuff that like, oh, you forgot about this is so ridiculous. And these, if you look them up, they're called Bell experiment loopholes. And it's literally the wildest crackpot ideas you can come up with. Like, oh, you are biased as a human being, like to influence the detector position or something like that, right? Like that's the kind of like extreme they would go to test this stuff. And they keep passing it with quantum mechanics coming out as the theory.
Yeah. I mean, like, I think the one that you're talking about, right? It involved setting a bunch of things up randomly, like around the world by people playing a video game. Is that right?
Yeah. A lot of it comes down to they don't want. So we talked about the particle on the left being measured in the vertical direction, and then the particle on the right measured at some angle, some different angle. What is that angle, and how do you set it? Because if you set it ahead of time, you can argue that there's some physical communication happening from the source, and the particles know where the detector is. You know, as ridiculous as that sounds, people want to rule that out. So you have to get them far away. You have to get that angle determined. So if the particle going to the left and the particle going to the right, say they separate at time t equals 0, you set your detector angle after the particles separate. So it's not prescribed into those particles. There's no possible way because the angle is randomly selected. Then it comes up with, well, how do you know it's actually random? You can't use a random number generator because they're not random. They're programmed by humans. And so they tried to get random input, like generators for these random numbers from people playing video games, like their key clicks. Like, I don't know, there's some algorithm that they use to get a number from the key clicks, and that determines what the angle is that the detector's set at. And then people were like, that's still not enough. So what they did most recently, I think last year, in 2018 maybe, they set up a source of particles on a roof of a science building. And then they set up a detector across town on the roof of a different college's building. And they set up the other detector, say the one that went to the right, on the roof of some bank. I think this was in Belgium or something like that, or no, Vienna, Austria. And so it's particles, I think it's laser light flying across town, right? Like shooting between roofs and detectors. And the detector's angles are randomized by looking at the light from a star that is 600 light years away. And so they're saying, okay, if there's some cosmic correlation between all this to convince us that quantum mechanics is correct, it must have happened 600 years ago because we're looking at the color of the starlight, the photon, like we're detecting one photon of starlight and saying, what color is it? What's the wavelength of that photon? And then that's determining our angle of our detector.
Yeah, and even if you like think about that even more, is it's not just like 600 years ago that star gave off, this particular photon. Mm-hmm. It's also that 600 years ago that happened, and then that photon hit our atmosphere,
right,
and went through Compton scattering and other effects, that would change its color,
right,
and ran into all these particles on its way down, and then boom, like hits the detector.
Yeah. Yeah.
So there's so many random
so yeah, this is the extremes we're going to. This is where we're at with like testing quantum mechanics validity, is like that sort of extreme. Like quantum's passed every test possible, and we're now at like, okay, let's check starlight randomization to like set our detectors up and like check if this is valid. I don't know. It's funny. And every time quantum mechanics comes out on top.
Yeah. So I wanted to add one thing tacked onto the end, but I didn't know if you wanted to talk about kind of Merman's counting version of this.
Yeah, I just wanted two points, I guess. So what we talked about of randomly selecting the angle between one detector and the other one, that's Bell's test. That's what he came up with for the experiment. Since then, in I think 1985, David Merman, who we've mentioned a few times here, he came up with a paper that's much more simple to understand, and it doesn't have to go into like an integral over density functions. And he says, instead of 2 detectors, use 3 detectors. And all 3 detectors are 120 degrees apart. So it spins, it's like a Mercedes symbol, right? They're equally spaced.
Is this, do you know the name of this paper?
Is it the moon one? I don't remember what the original paper is.
Well, there is a paper that I read. It's called Is the Moon There When Nobody Looks?
Yeah.
Reality and Quantum Theory. But that one only has 2 detectors in it. But it's a good read. But okay.
I think it's 2 detectors, but they each have 3 settings or something like that.
Yeah,
I think
that is it.
That's the difference, is instead of an arbitrary angle, it could be one of 3 angles, either vertical, or 120 degrees, or 240 degrees. And then another 120 gets you back to 360, so you start over. So it's 2 particles, 2 detectors, but only 3 settings possible. And that's his simplification of Bell's experiment. And that's in the mid-'80s. And that's the one, if you watch like Veritasium video, that's basically what he talks about. A lot of the pop science ones are using that explanation of Bell's theorem. So that happened much later. Bell's original paper in 1964. So 21 years later, Mermin comes out with his 3-position detector, and there's 2 particles, 2 detectors, but only 3 positions. And each detector can measure up or down. That's the other place it gets really confusing, because people talk about Alice and Bob as the 2 detectors, and then particle A and B are 1 and 2, but then position 1, 2, 3, up, down. Sometimes you use colors for the 3 positions, red, green, blue as light bulbs, and is it on or off? It's not that complicated if you write it out, but like it's a lot to keep track of in your head.
Yeah.
So that's Mermin. That's the simplification Mermin added in the 80s. And again, that's what if you watch most videos, I think that's usually what they're talking about. Yeah, the 3 positions of 2 detectors.
We'll post this paper. I think we can post this paper. We'll post this paper on our...
Yeah, I found it for free online.
We'll link to it so you can read it.
The next simplification, though, happened, and this is more of an experimental simplification, less so of a conceptual one. It's a little bit... Again, it's simpler in that you can just kind of count things, but it uses 3 particles. And this is not a Mermin simplification. Instead of 2 particles, it uses 3. It's 3 guys' names, and it's usually called GHZ experiments. And that was around 1990 that they came up with this setup for an experiment that could be done. And again, it comes down to a Bell type experiment, but they're using 3 particles. And that essentially simplifies things quite a bit. And Mermin explains it very well with his, there's the thing and there's the stuff left behind, back to the EPR discussion. So the thing that you can measure is one of the 3 particles, and the stuff left behind are the other 2 particles. And it comes down to straight counting. Like if there's 3 detectors, 3 particles, I think each detector has 2 positions. I'm pretty sure that's true. And that detail I don't remember actually. But anyway, it's like if you have of your 3 detectors, if it's a 1, 2, 1, for example. So detector 1 is set to knob 1, detector 2 is set to knob 2, and detector 3 is set to knob 1. There's only 2 options for the detector knob settings, but there's 3 detectors. It's something like if it's 1, 2, 1, then you're always going to get an odd number of spin ups from the 3 particles being measured. Something like that. Like it's just like a combinatorics kind of simplification of it. And you can use that for spin measurements and come up with a pretty simple experiment to test this stuff. And again, it's just straight counting. So that's why it's simpler. I don't see very many pop science videos or papers talking about it, but most of the experiments, as far as I understand these days, are using GHZ. And the Z is Zeilinger. I know that because he comes up in a lot of the experimental setups. I forget the G and the H. I could look it up real fast, but
yeah. But so you kind of just like in the Mermin paper, he just walks through. Okay, like here we collected some data, and he kind of gives you some, a little bit of data, and he says, okay, look at this feature of the data, and look at this feature of the data. And the only way that these 2 features can be both true is if quantum mechanics, he says the only way that both of these can be true is if we don't have a hidden variable system. Right. So do we have anything else to say on?
No, I'll just give you the 3 names. It's Greenberger, Horn, and Zeilinger. So Greenberger and Horn are the GH, part of GHZ experiments, but those are 3 particle experiments.
A couple of things I wanted to add.
Okay, I got one thing to add, but go ahead.
Okay, go ahead.
Well, it's not super related, but you did say hidden variables. The key part, and Bell says this explicitly, he says, no physical theory of local hidden variables can ever reproduce the predictions of quantum mechanics. that keyword local there, that comes back to the special relativity of being able to communicate information faster than the speed of light. Basically, it needs to be influenced some way in a less than the speed of light sense. There are non-local hidden variable theories of quantum mechanics, and we'll talk about one of them soon in a later episode with pilot wave theory. That's an example of a non-local hidden variable theory that is consistent with quantum mechanics. So that keyword local is pretty important.
Right.
That's all I wanted to say.
Yeah. I was going to mention that too. That's what leads to kind of maybe some Bohmian mechanic possibilities. So also just to note two things. One is along that regards is I just saw this really quick. And so I don't know how it works, but as a reminder, we're recording this after we recorded the Bohmian mechanics episode.
Yes, that's true.
But one of the things I saw, I think it was on a Wikipedia page somewhere, was that there's actually a generalization of this. And so it's not just hidden variables, but what was it like? Counterfactual somethings. There's a more generalized form of Bell's theorem that is bigger than just hidden variables. And some people apparently claim that theory makes pilot wave theory impossible, or that generalization.
Interesting. Okay. I haven't heard of that.
Yeah, it was just like one quick snippet I read somewhere when I was doing this, but I thought that was kind of like, oh, okay. The other thing I wanted to mention is, especially like, we're talking about spins or polarizations and stuff. And if you've kind of been up on, quantum news and stuff in the last, I don't know how many years, but I feel like it's been fairly popular in like at least the last 10 years. You've heard about entanglement. And that's essentially kind of what we're describing, right? Is that these two particles are entangled when they leave from, the center part, they go off in their different directions. There's a lot of like stuff going on with this, particularly I think in quantum computing. But I want to just point out that like Einstein and is it Podolsky?
Yeah,
and Rosen didn't know that was a thing. Like when they wrote their paper, they weren't.
That language didn't exist. It wasn't part of the fundamental teachings of quantum mechanics at the time.
Yeah, exactly. Because like I feel like if you've kind of approached this from not from a historical angle, but from like the reverse angle, you go, okay, entanglement is a thing. And then you'd read about this and be like, wait, why is this a problem? We already have entanglement. So, just like entanglement's pretty much accepted essentially because of Bell's theorem.
Yeah. I mean, I think entanglement really sets the stage for Bell experiments. Like that you can even do this stuff is based on entanglement. And it comes back to the glove. Like the gloves are kind of you consider like left, right, like they're entangled in the sense that whatever one is, the other one has to be the opposite. Again, the difference is the physics of gloves is well understood, and there's no superposition of glove, right? But particles, we have evidence that there is superposition of states of particles. What's the evidence? You can do the double slit experiment as one example, where it's like, it kind of comes down to the same type of question. Now I'm opening up a big can of worms with double slit experiment, but I think it's fundamentally linked in that the question you ask affects the answer you get, if that makes any sense. And I think it does. Like if you ask, what's your wavelength, and send it through a double slit experiment, the only way that answer gets resolved is if the particle went through both slits, right? Like you have to analyze it using two slits simultaneously, being the particle going through both and interfering with itself, the wave function interfering, and get your answer. But if you ask, did you go through the left slit? You'll get an answer that is a yes or no answer to that. But you did a different test where you said, what's your wavelength? And to answer that, you had to go through both of them, and it gave you an answer for the wavelength. Yeah. I don't, it's a loose connection, but it's a connection in my head between that and the fundamental definition of reality. that like your question determines the answer. And Merman ends his talk with a quote, or I think it's the title of a paper. I forget the person's name, but the title of the paper was something like experiments that aren't done don't have results, something like that. Like you can't talk about experiments that would have happened. You can only talk about experiments that happen. So these like unanswered questions don't give you, you can't talk about the results of tests that aren't done, right. Which is sometimes an argument people use to discredit like the entanglement or the Bell's theorem. Yeah. Now I'm rambling, but it's a loose thread connected in my head to this stuff.
Right. So, I mean, I guess the major takeaway is Bell devised a method to say essentially whether this quantum uncertainty was a real thing or not. And we ran the test and it looks like it is right.
I mean, as it stands, yep, spooky actions at a distance are what actually happens.
Right.
Sorry. And people are like, oh, Einstein was wrong because he thought it wasn't happening. I'm like, well, no, he was just highlighting the fact that the quantum mechanics says it happens, but it breaks intuition. And so what's going on here? So what is there anything that's real? Can we even talk about reality without having experiments? Does anything exist outside of us making measurements? And what does making a measurement even mean? So
yeah. I mean, I think
that's where we're stuck.
There's a whole metaphysics conversation that can be held here,
right.
That's still going on to this day with all sorts of, input from different people.
Right.
What kind of, outside of this episode, I don't think we've talked about this, but, the whole issue, or Einstein had issue with the Copenhagen interpretation of quantum mechanics. Mm-hmm. And, I think in a later episode, we're going to talk about kind of the Bohmian mechanics is a different kind of viewpoint of quantum mechanics. And there's, many worlds theory of quantum mechanics. And there's kind of like different interpretations of this. And that's kind of where this is getting to. And that's not a place like that is well, people are still arguing about that to this day, like really smart people.
Right. Yeah, that was fun. I'm glad we got it. Hopefully this recording exists after we stop recording.
Yeah. It should. And you could find again us at thehyperfine.com.
Mm-hmm. The Hyperfine, THE at the front, unfortunately.
Yeah. Or you can find us on Reddit at, what's our subreddit?
It's just r/thehyperfine.
Okay. Yep.
Again with the.
Yes. It must include the.
Mm-hmm.
And you can find me. I have a new Twitter handle.
Ooh, look out. What is it?
My friend came up with it. It's pretty awful, but that's kind of why I like it.
All right.
It's Phyzaks. PHYZAKS.
Well, there it is. I'm at Like Tortilla. My last name is Padilla, Derek Padilla, Like Tortilla. So you won't mispronounce it in the future. And you can find me on Twitter. I don't know. I'm leaning towards Instagram more, but anywhere I'm around as Like Tortilla.
All right. Well, see you next episode.
Yeah. See you next time.